Hello, I'm going to do programming exercise to logistic regression for machine learning class. Here we have an introduction. We will implement logistic regression and apply it to the two different data sets. All the information we need solving this and all the codes we'll be implementing will take place within this notebook. Before making the exercise, we need to import important libraries NumPy, Matplotlib, and SciPy. We have an outline and here is logistic regression. In this exercise, we build a logistic regression model, and we suppose that we are administrator of the university and want to determine each applicant's chance of admission based on their results on 2 exams. We have historical data from previous applicants that we can use as a training set for logistic regression. For each training sample, we have the applicant scores on 2 exams and admissions decision. Our task is build a classification model that estimates an applicant probability of admission based the scores from 2 exams. It's loading our data. Okay. Visualizing the data before starting implement any learning algorithm. Always good to visualize if possible. We display the data on 2-dimensional plots with column plot data. We left plot data empty. In here this part is empty, so we're gonna write this in here. Okay. Actually, let me stop the video here because it's gonna take a while. After I finish writing the code, I will continue. Now I write the code, and after we run plot data xy pyplot x label exam score 1 pyplot y label exam 2 score pypilot legend admitted not admitted. We have this table here, the admitted and not admitted. We have exam 1 score in here and exam 2 score in here. In here we have a warm-up exercise for sigmoid function. Before we start the actual cost function, recall that the logic regression hypothesis is defined as h0x equal g theta t x, where function g is sigmoid function. The sigmoid function is defined as gz equals 1 over 1 plus e to the minus power of z. it's the negative power of z. Our first step is to implement the function sigmoid so it can be called by the rest of our program. When we finished, try testing few values by calling x sigmoid in a new cell. For large positive values of x, this sigmoid should be close to 1, while for large negative values, this sigmoid should be close to 0. Evaluating sigmoid 0 should give you exactly 0.5. Your code should also work with vectors and matrices. For a matrix, our function should perform the sigmoid function on every element. And we will implement the functions in here. Let me stop the video and write the code down here, and then I will continue. Okay, the g function now is here. Now we will run the code, and here the following cell evaluates the sigmoid function at z0. You should get a value 0.5. You can also try different z's. Let's see. It works fine. In here we have a cost function and gradient, and now complete the code for the function cost function to return the cost and gradient. Recall that the cost function in logistic regression is, we have a j theta function in here, and the gradient of the cost is a vector of the same length as theta, where jth element for j equals 0, 1 to n is defined as follows. This function is here. Note that while this gradient looks identical to linear regression gradient, the formula is actually different because linear and logistic regression have different definitions of h theta x. Okay, we will implement the functions in here. So let me stop the video and I will implement these two functions. After that I will continue to recording. Okay, now here we are with the implemented functions. We define an h equals to sigmoid x dot function theta t, and the j function in here equals to 1 over n times numpy sum minus y dot numpy log h minus 1 minus y times dot function of mp log 1 minus h, and we have a gradient function in here, grad 1 over m times h minus y minus dot x, and let's run it. Once we are done, we call function in this cell. Oops, we have an error. Okay, we made a mistake in here. We should use uppercase X. Now it works fine. Python is case sensitive language, so we have a mistake in here. We use uppercase X and the error is gone. Now we have learning parameters using scipy.optimize. We have here the intro for learning parameters, and let me read it after stopping the video because it takes a while. After that I will continue the recording. Okay, so here we use scipy optimize. Here is some methods and here's the code. Once optimize minimize completes, we want to use final value data to visualize the decision boundary on the training data as shown in the figure below. To do, we have written function plot decision boundary for plotting decision boundary on training data. We do not need to write any code plotting decision boundary, but the exercise also encourage us to look at the code in plot decision boundary to see how to plot such a boundary using the theta values. You can find this function in the utils file which comes with this assignment. So let's run it. I don't know why we have this warning. Let's continue. Okay, we have same figure. In here we write a code here. After learning the parameters, we can use the model to predict whether a particular student will be admitted. For a student with an exam 1 score of 45 and an exam 2 score of 85, you should expect to see an admission probability of 0.776. Another way to evaluate the quality of the parameters we have found is to see how well the learned model predicts on our training set. In this part we complete the code in function predicts. The predict function will produce 1 or 0 predictions given a dataset and learned parameter vector theta. So we round the value 1 to 1 or 0. Okay, let me implement the code and after that I will continue the video. Okay, here is our code. We return p value. We round this value, it's numpy. So our function will produce 1 or 0. We take a sigmoid function and send the x and dot production matrix multiplication with theta and theta transpose. So let's run the code and check if we done correctly. So we have for a student with scores 45 and 85, we predict an admission probability of 0.776. Expected value is 0.005 plus or minus 0.002. So our train accuracy is 89 percent, and expected accuracy approximately is the same. So we done it correctly. In here we make regularized logistic regression. In this part of exercise you will implement regularized logistic regression to predict whether microchips from a fabrication plant passes a quality assurance during QA, and test to ensure it's functioning correctly or not. Suppose we are the product manager of the factory and we have to test results for some microchips on 2 different tests. So we implement logistic regression here too. Here we have visualized data. Our data is here, and feature mapping. One way to fit the data is better is to create more features from each data point in the function map feature defined in the file utis.py. We will map the features into all polynomial terms of x1 and x2 up to the 6th power. We have here map feature x, and as a result of this mapping, our vector of 2 features, the scores on the 2 QA tests, has been transformed into 28-dimensional vector. A logistic regression classifier trained on this higher dimension feature vector will have more complex decision boundary and will appear nonlinear when drawn in our 2-dimensional plot. And while the feature mapping allows us to build more expressive classifier, it also more susceptible to overfitting. In the next parts of the exercise, you will implement the regularized logistic regression to fit the data, and also see for yourself how regularization can help combat the overfitting problem. Let's run this box, and we have cost function and gradient function in here. We will implement this function in your code gear parts. I will implement the code. When I implement, I will stop the recording for length of the video. So after I implement, I will continue. Okay. Now I implement the code. We have h sigmoid x dot theta t. This line computes the hypothesis function h by applying the sigmoid function. The linear combination of input x and parameter vector theta, and we have temp lines. Then we create the temp as a copy of the parameter vector theta, and the first element is set to 0, and this is done for excluding regularization for the bias term in the subsequent calculations. And for these functions we define j 1 over m times mp sum blah blah blah, and we here numpy sum of the minus y dot function numpy log h, this function, and we implement the function in here minus 1 minus y dot production of numpy log 1 minus h plus lambda parameter over 2 times m times numpy sum numpy square temp, and in here we have gradient functions, and grad is equal to 1 over m times h minus y dot x, and grad is equal to grad plus lambda over m times temp. The first part of the equation calculates the gradient without regularization, and this part represents the gradient of the unregularized logistic regression respect to theta, and the second part adds the regularization term to gradient, which is lambda over m times temp, this part, and temp is the parameter vector with the bias term set to 0, and it is used to exclude regularization for the bias term. So let's run it. Once we are done with the cost function reg, we call it below using the initial value theta, and also another test case where theta is all ones. As you can see, code is working, expected, and our values are same. In this part, learning parameters using SciPy optimize minimize, plotting the decision boundary to help you visualize the model learned by this classifier. We have provided the function plot decision boundary, which plots the nonlinear decision boundary that separates the positive and negative examples. In plot decision boundary, we plot the nonlinear decision by boundary computing the classifiers predictions on an evenly spaced grid, and then enter a contour pilot where the predictions change from y equals 0 to y equals 1. Optional ungraded exercises. In this part of the exercise, you will get to try out different regularization parameters for the dataset to understand how regularization prevents overfitting. Notice the changes in the decision boundary as you vary lambda with a small lambda. You shall find that the classifier gets almost every training example correct, but draws a very complicated boundary, thus overfitting the data. See the following figures for the decision boundaries you should get for different values of lambda. Okay, here we have overfitting. We have decision boundary with regularization. Decision boundary with too much regularization. This is not a good decision boundary. For example, it predicts that a point at x minus 0.25 around here and 1.5 is accepted is here. Y equals 1, which seems to be incorrect decision given the training set. With a larger lambda you shall see a plot that shows a simpler decision boundary which still separates the positive and negatives fairly well. However, if lambda is set to high value, you will not get a good fit and the decision boundary will not follow the data so well, thus underfitting the data. Okay. Let me check that part, and after that I will continue with it. Okay, I checked it, but I think the error inside the exercise file, not inside the code, which I cannot fix for now inside the exercise screen. So that's it for this exercise. Thank you for watching. Have a nice week.